Today's calculus lesson is about estimating finite sums, and then the definite integral and area. So let's read this first problem. The velocity of a toy car is shown in the graph. The equation for velocity is given by v of t equals 2t times 0.8 to the t. Find approximately the distance the car travels from t equals 2 to t equals 10 by counting squares. So let's talk about this. Distance traveled is always going to equal the rate times the time. So how fast are you going and how long are you going at that speed? So if we look at this axis, this is time and this is velocity. So at any given point, at time 2, this is the speed this car is going. At time 4, this is the speed, and so on. So what we're going to do is multiply the rate times the time, which geometrically is the area of one of these squares. So we're interested from 2 to 10. So we're going to count up all of these squares. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I counted 43 whole squares, or mostly whole, some of them are a little cut off. And then I have these partial squares. So just estimate to the nearest tenth about how much you think each box is. So like this one, it's a little bit more than half, so I'd say it's like 0.6. This is less, and so on. So maybe about 0.4, maybe 0.7. It's about half, 0.5, a little teeny one, so we'll call that 0.1. Again, this is just a rough estimate. There's no, and let's call that 1.6. So I've got the 43 whole squares, and then a 0.6, a 0.4, a 0.7, 0.5. And if you count them different, like I said, that's okay. Okay, so how many squares is that? That's approximately 46.6 squares. Now let's look at the units here. If I have one square on this dimension, looking at the graph, each of those is going to be 1 second. On the y-axis, each square is 1/2 feet per second. So the area of the square is actually going to be 1/2. If we multiply feet per second times second, that's going to be 1/2 of a foot for each square. So I'm going to take my 46.6, multiply that by 1/2 to get about 23.3 feet. Same graph, but now we're going to find approximately the distance the car travels from t equals 2 to t equals 10 using a left Riemann sum using 4 intervals of even width. Okay, and then we'll answer that follow-up question. So a Riemann sum. So again, we're going from 2 to 10, and we're going to break this up into 4 equal pieces. So that's going to be from 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So we're going to go ahead and draw vertical lines at all of those locations. Okay, a Riemann sum is a way to approximate the area under the curve using rectangles. A left Riemann sum, the connections for the rectangles are going to be on the left side. So we're going to start on so this first one is going to go from here to there. This one like that. Next one like that. Next one like that. So the rectangle is going to be evaluated at the leftmost point. Okay, then we're just going to find the area. So we're going to add the area of each of the rectangles. So my distance is going to be, the width of the rectangle is 2. The height of the rectangle is the velocity evaluated at 2. The second one's width is 2. The height is the velocity evaluated at 4. The next one, the velocity, width is still 2, the velocity evaluated at 6. And then the width is 2 and the velocity evaluated at 8. So there's the area of each of my rectangles. We're then going to use the calculator to help us out with these velocities. So in the calculator, I've typed in my equation given to us at the top of the paper here. So we've got 2, instead of t, I'm using x, 2x times 0.8 to the x. Now you can use the evaluate feature. Since I'm going to evaluate it at 2, 4, 6, and 8, I'm actually going to use the table. So if we go to second table set, start at 0, make sure your delta is 1 because I just want whole numbers. And then I can use these numbers from the table. We would want as accurate as we can, but for right now, let's just use 3 decimal points. So we need the at 2, at 4, at 6, and at 8. And I'm going to fill that in the notes now. So these are the values pulled from the chart, and you could also use the y1 evaluated. That works too. So if we type all this in, we get approximately 23.334 feet, which is pretty close to our last guess. Okay, we're going to continue to estimate this in different ways. This next one, we want a right Riemann sum. So on the graph, we're still going from 2 to 4, or 2 to 10, in those same subintervals. 8 and 10. This time the connections are going to be on the right-hand side. So from 2 to 4, we're going to evaluate this one at 4. This one we're going to evaluate at 6, at 8, and at 10. So the area of the rectangles, 2 times the velocity evaluated at 4, 2 times the velocity evaluated at 6, and 2 velocity at 8, and 2 times the velocity at 10. Again, using the calculator. Fill in those values. This one gets me an approximation of about 22.509 feet. For the next one, we're doing a midpoint Riemann sum. So we're still going to draw our lines. But rather than evaluating them at the right or the left, we're going to evaluate at the middle. So if we're going from 2 to 4, the middle is going to be at 3. So draw a dot. That's where we'll evaluate this one. Between 4 and 6, we're going to evaluate at 5. Between 6 and 8, we're going to evaluate at 7. And between 8 and 10, we're going to evaluate at 9. So the width is still 2, and then we're evaluating at those midpoints rather than the endpoints. You can use the calculator to get those values. When evaluated, this one's approximately 23.212 feet. We're going to do this one more way with something called the Trapezoid Rule. So on the graph, we're still going from 2 to 10, and we still have 4 even intervals. But rather than making rectangles, we're going to make trapezoids by connecting the endpoints. So there's our trapezoid from 2 to 4, from 4 to 6, from 6 to 8, and from 8 to 10. Okay, the area formula for a trapezoid from geometry is 1/2 times the height times the sum of the bases. This one, these are trapezoids. Trapezoids are defined by two parallel lines and two not parallel lines. So the two parallel lines are always going to be these vertical lines. So the bases are going to be those heights. The height of each of these rectangles is going to be the distance between those bases. So our distance, we're going to have 1/2, so we're doing 4 of these formulas. The height is going to be 2. The sum of the two bases, this is going to be v of 2 plus v of 4. And we're going to repeat this for all of them. I'm just going to work vertically just so you can see them all. So we're going to have 1/2 times 2. The next one from 4 to 6 is going to be v of 4 plus v of 6. Next one, 1/2 times 2. We're in this rectangle now, or this trapezoid. So v evaluated at 6 plus v evaluated at 8. And lastly, from 8 to 10. Okay, then you plug in the corresponding numbers and add all of these up. This one gives us approximately 22.921 feet. Okay, now there is a way to do this in your calculator. I'm going to share some notation and then we're going to define it and talk more in depth about it here in a second. This is involving the integral from 2 to 10. This is what's called a definite integral. Okay, so we can do this in the calculator. This finds the area of v of t from 2 to 4. So in the calculator, remember that our function is stored in y1. So I'm going to go just to my home screen here. If you go to alpha f2, in this menu, underneath the derivative which we've used, is fn int. So we want fn int from 2 to 10 of our y1, and we put an x there. Gives us 23.242 feet. So our approximations were all pretty accurate, or pretty close anyway. Now I want to talk about whether the Riemann sums are an overestimate or an underestimate. For the right and left, that's going to depend on whether the graph is increasing or decreasing. So first we're going to look at if the graph is increasing, if we have a left Riemann sum versus a right Riemann sum. So the left Riemann sum is going to be calculated from the leftmost point. So if I look here, we have area that's under the curve that's not being accounted for. So a left Riemann sum is going to be an underestimate. Okay, versus a right Riemann sum. Okay, now I'm adding in extra area, so this is going to be an overestimate. Okay, that will change if we're talking about a decreasing function. So a left would look something like this. Okay, now we have extra area, so this will be an overestimate. Versus if we joined our points at the right, okay, pretty clearly we're not including all of that area, so that would be an underestimate. Concavity will affect whether a trapezoid is over or under. So if I'm concave up and I wanted to do this trapezoid rule, okay, all of those bars are above. So this is going to be an overestimate for a trapezoid. Versus if our graph is concave down and I drew our trapezoids. And these are just rough approximations here. Okay, now we've got area unaccounted for. So a trapezoid rule will be an underestimate if it is concave down. Now let's talk more formally about the definite integral. Right now, we're just going to kind of loosely define this as the area under the curve. So I'm going to go through and kind of develop what all of the different pieces of this definition are going to be. Okay, so let's say we have some function here. Okay, and I want to approximate the area from here to here. Okay, well, so far we've done, rectangles. Okay, but we know that that has some issues with it. So what we want to do is really get as many rectangles as I can, because if I make them super, 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 super skinny, okay, that approximation is going to be a whole lot better. All right, so let's widen our net again. So we'll get to making these infinitely small in a second. Let's talk about the area of one of these rectangles. Well, the area is just going to be the length times the width. The length we're going to call delta x, how far apart this x value is from this x value. The height, let's call this x1, is going to be the function value, whatever I plug in x1. Okay, call this one x2, this height would be f of x2, and so on. Okay, so going to summation notation. So we're going to start with a k value of 1. And we're going to go to n number of rectangles. Okay, we're going to have n rectangles. So starting at k equals 1, our height of each rectangle, so the area of each rectangle, is going to be f of xk times delta x. Okay, that would give me the Riemann sum. It would be all of these different rectangles. If I had n rectangles and we evaluated it at x1, x2, x3, and so on. Okay, well, let's think about this. What I want to have happen is really kind of two things. One, I want this to get as big as possible. Okay, going with that, I want delta x to be as small as possible. So you'll see this written in several different ways. Some will give it where you're looking at the limit as this goes to 0. We're going to do this as the limit as n goes to infinity of our Riemann sums. Okay, so that's going to be our definition. All right, so let's put that more formally. Okay, a Riemann sum is the sum of our rectangles. So it's going to be the sum from k equals 1 to n of f of xk times our delta x. Okay, the definite integral the notation is the integral from a to b of f of x dx. And hopefully you can kind of see some The sigma becomes the integral notation. F of xk is f of x. Delta x becomes dx. Those are all not accidents. This is going to be the limit as n goes to infinity of our Riemann sums. And that is the definite integral. Okay, so we're going to write these integrals as the limit of a Riemann sum. So let me illustrate this out, and then we'll come back here. All right, so we have the integral from 3 to 5 of x squared. So I'm just going to draw a curve in here. Okay, well, as a Riemann sum, what we're doing is we're taking this and we're approximating the area using rectangles. Okay, we have n rectangles. Okay, so looking at this specific case, and then we're going to go back to the paper and write it more formally. Okay, the area of these rectangles is going to be the width times the height. Okay, so let's first talk about the width. Okay, our delta x. Okay, well, I'm going from 3 to 5, and I'm cutting that into n number of rectangles. So the width is going to be 5 minus 3 over n, or 2 over n, because I'm taking a distance of 2 and cutting it into n different pieces. So this distance here is going to be 2 over n, this distance is going to be 2 over n, and so on. So my delta x is 2 over n. Okay, the heights. Okay, I'm going to call this here, this is x1. The height is going to be f of x1, or it's going to be x1 squared. So here we've got 3, and I'm adding on 2 over n. Okay, that's my x. We started here, I add on 2 over n. So this is going to be 3 plus 2 over n squared. Okay, my next one. My x value is going to be 3 plus 2 over n's, because we've got 1 here and 1 here. So this height is going to be 3 plus 2 over n squared, and so on. So what's going to happen is we're going to continue to add on an additional 2 over n as we go. Okay, so let's put this in the sigma notation. Okay, so using the sigma notation, we're going to have the limit as n goes to infinity of the sum when k equals 1 to n number of rectangles. Our heights are going to be 3 plus 2 over n k squared, and I multiply that by the heights, or the widths, which was 2 over n. Okay. So the parts, we're taking k, and that's going to increase my x value. Okay, so we're adding on 1 2 over n, 2 over n's, 3 2 over n's, and so on up to n number of n's. The 3 came from the starting value because we started at 3, then we started adding on those 2 over n's, and then our height is just 2 over n. Okay, so that's kind of the structure here. So here, we're going to have the limit as n goes to infinity, k equals 1 to n. Okay, our heights are going to be the square root. The x value is going to be 2 plus this time our widths, we're going to have 6 minus 2 over n, or 4 over n. So we're going to add 4 over n k times plus the 1 times the widths of our rectangles are that 4 divided up into n pieces, because we're going a total distance of 4, we are breaking it up into n different rectangles. So let's do one more of these. Okay, so this one we've got cosine of x, so this is going to be cosine. We'll have our starting value at -2. We're going to add on our distance is 3, so we're going to add on 3 over n k times, and our widths are 3 over n. Now the good news here is you will very, 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 very unlikely have to actually write this out. What your job is going to be is on a multiple choice question, matching it. Okay, now going the other direction, we're going to have the integral. We've got a 2, so that's going to be our starting value. If we're cutting 4 into n pieces, that means my distance between my bounds are going to be 4, and then my function is just going to be x cubed. Okay, here we're going to have the integral starting at 1. If our distance is 5, we'll end at 6. My function here is going to be 3x minus 4, and then we'll do our dx. So here's how you might see this as a multiple choice question. So which of the following limits is equal to the integral from 3 to 5 of x to the 4th? Well, they all have the function. We can see that. It's all x to the 4th. The thing that's changing is these two. Okay, we know if we're going from 3 to 5 that our delta is going to be 2. So these are out, and this one needs to have a 2 as well. So it's going to be this one. So again, it doesn't mean you have to come up with this. You just have to understand what each of the different parts mean in order to make a match. Okay. Now we're going to do a Riemann sum from a table. So the table shows a continuous function using the subintervals from 1 to 3, 3 to 6, 6 to 8, 8 to 12. With these different values, we're going to approximate the integral from 1 to 12 using the trapezoid rule, a left-hand Riemann sum, and a right-hand Riemann sum. So the trapezoid rule is going to be 1/2. The height of each of the rectangles is going to be the change in x values, the width. So this one's change is going to be 2, this one's 3, this one's 2, and this one's going to be 4. So my width is 4. For the trapezoid, we use both of the endpoints. So 4 plus 5 plus 1/2. The second one's width is 3. 5 plus 1. Our third trapezoid, 1/2. Its height is 2. We have 1 plus 3. 1/2 times 4 for this one. 3 plus 4. When you plug all that in, you'll get 36. The left-hand Riemann sum, we're doing rectangles now. So it's going to be the width times the height, and the height is going to be evaluated at the left side of the rectangle. So my first width is 2. The height for the first one, we're going to evaluate at the low end, so 4. The next one's width is 3. Its height is 5. The next one's width is 2. Its height is going to be 1. The last one's width is 4, evaluated at the left side at 3. All of that together is 37. The right-hand Riemann sum, we're going to have the same widths, 2, 3, 2, 4, but now we're going to evaluate at the high end of the range, at the left-hand side, or on the right-hand side. So we're going to have 2, times 5 plus 3 times 1 plus 2 times 3 plus 4 times 4 is 35. So we've defined definite integral in a couple different ways, but the basic idea is the integral is the area under the curve. So what we're going to do here is make a graph and then use geometry, good old geometry, to find the integral value using area. Okay, so our first one, we have the integral from -2 to 1 of 5. So if I were to graph the function y equals 5, that's just going to be a horizontal line. So we want the area from -2 to +1. So this is our area that we are going to find. This is going to be the definite integral. So we'll multiply the width times the height. So this is 3, this is 5. So this area is going to be 3 times 5. So the integral is going to be 15. Here we've got from 2 to 4 of 2x plus 1. So we'll go ahead and graph that. Okay, so 2x plus 1, we're going to cross at 1 and then go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I switched my colors. So we want the integral from 2 to 4. Okay, so this one's going to be a trapezoid. So the area of the trapezoid is going to be 1/2. The height of the trapezoid is going to be 2, and then the two bases are going to be the two different function values. So at 2, we plug in 2, we're going to get 5. If we plug in 4, 2 times 4 is 8 plus 1 is 9. So this one has an area of 14. Okay, this one is the area formula for a semicircle with a radius of 5. I'm going to go 5, 5, -5. So my function is just a semicircle, and we want the area from -5 to 5. So this one's area is pi r squared, 1/2 pi r squared. So this is going to be 25 pi over 2. Okay. Our next one, x from -1 to 4. So y equals x. Just a straight line here. Y equals x. This one, we're looking from -1 to +4. So it's this and it's this. So we have two triangles here, but one of these triangles is below the x-axis. And if you're doing an integral, if it's under the x-axis, this area is going to be negative, this area is going to be positive. So this is going to be this triangle, which is going to be -1/2 base times height, which is 1 and 1. But it's got to be negative if it's below the x-axis. And then here, we'll have plus 1/2, 4, times 4. So we'll have 16 over 2, which is 8, minus 1/2. So this integral is 7.5. So even though we're using area, the area I shaded isn't 7.5, but the integral is 7.5. Okay. The absolute value of 2x plus 1. There's several ways that you can think about graphing this, but I'm going to start by just graphing the line 2x plus 1. I'll go here, but then it's going to bounce up because it's the absolute value of that line. So my next dot is going to be here and here. So I want the integral from -3, so there's -1, -2, from -3 to +2. So that's going to be two different triangles. The width of the rectangles is going to be 2.5, so 1/2. This one is 2.5. The height, if I plug in -3, that makes this -6 plus 1 is -5. Absolute value of that's going to be 5. This one's also 2.5 and 5, so I'm just going to plop a 2 in front of that to say I have two triangles, or you can add them together. This is going to be 12.5. Okay. This one's integral. We're going the integral from 0 to d of f of x. So all we're going to do is we have above, below, above. So this is going to be whatever the area 1 is minus whatever the area of 2 is plus what the area of 3 is. This is the same thing but with values. So we want the integral from a to c. So a to c is going to be 1.8 minus 2.3, which is going to be -0.5. From a to d is going to be 1.8 minus 2.3 plus 1.4, which is 0.9. Okay, next one, I am again going to go ahead and graph this piecewise function. So when x is greater than 0, we have the line 2x. So 0, 0, up 1 over, 2 over. And then when it's less than it, we have -3. So we have a closed dot here, an open dot here. So there's our graph. So the integral from 2 to 3, so here's 2, here's 3, that's going to be a trapezoid. So that's going to be 1/2 the width of the trapezoid, the distance between 2 and 3 is 1. And then if I plug in 2, we get 4. If we plug in 3, we get 6. So this is half of 10, which is 5. From -5 to -2, that's going to be a rectangle. It's going to be negative because the area there is negative. The width of the rectangle is going to be 3 between 5 and 2, and the height is also 3. So this integral is -9. From -3 to +2, we have to break that into two parts, the rectangle and the triangle. So from -2 to 0, that's going to be a -2 times 3 for that rectangle. Sorry, -3. because the width is, we're going from 3 on, sorry, plus the area of the triangle, which is going to be 1/2. The base of the triangle is going to be 2. The height of the triangle is going to be up at 4. And it may help to graph this. I just didn't want a bunch of graphs on the same thing. So this ends up being a -5. And I realized you haven't been able to see any of that. So we have -3 to 3 for the rectangle. And then 1/2, 2 times 4 for the triangle gives us a total of -5. Okay, this one's kind of funny. This one, if we factor, is going to be 3 minus x, 3 plus x over x minus 3. Well, these are basically the same but opposite, so this is really the same as a -1. So this is going to be the integral from -5 to 6 of -x minus 3. So that's just a line. I'm going to go ahead and draw that line. So here's the line, -x minus 3. Have a negative slope, negative y-intercept, and we want the integral from -5, which is going to be right here, to 6, which is all the way here. So again, we have two triangles. One's above the x-axis, one's below. For the one above, we're going to have a positive 1/2. That's going to be 2 times 2. Below the x-axis, we're going to subtract that triangle. So 1/2, this is -3 to +6, so that's going to be 9. And the height's going to be 9. So this ends up being, if you plug it all in, -77 halves. Okay, our last set of problems here says if the integral from 0 to pi of sine of x is 2, we're going to use that information to find some various things. So let me graph this. So sine goes from 1 to -1. Okay, so there's sine. So this is telling me that the area from 0 to pi is 2. Okay, so from that, we can answer some other questions. So if the integral from 0 to pi is 2, we want from pi to 2 pi. Well, this is going to be the same area, but negative. So this is going to be -2. For b, the integral from 0 to 2 pi, so from here to here, is going to be 2 minus 2, which is going to be 0. From 0 to pi over 2, well, there's pi over 2. So it's just going to be half of that, which is going to be 1. For 2 plus sine, we're going from 0 to pi, so what's going to happen here is the bump is going to go from here to here. So this area is going to be 2, but we still need this area as well. So we're going to have the 2 plus the area of this rectangle, which is going to be 2 times pi. Okay. The integral from 0 to 2 pi of 2 times sine of x. Graphically, it's going to change the amplitude. There is just a rule for integrals that if you're multiplying by a constant, you can pull that constant out. So this is going to be 2 times 2, which is 4. This one just shifts everything to the right 2. So we're going, here's 2, here's pi plus 2, and there's sine of x minus 2. So this is just 2. From -pi to pi, So from negative pi to pi is going to look like this. So that area is going to be 0. Okay, this one, x over 2. So you have to think back to pre-calc. The period of this is going to be 2 pi divided by 1/2, which is 4 pi. So rather than it doing one of these cycles from 0 to pi, it's going to go from 0 to 2 pi. So it just stretches it. So this is actually still going to be 2. And then the last one, 0 to pi of cosine. Cosine starts at 0, goes like that. So whatever this area is, which is 1 and 1, they are going to cancel each other out and be 0. So that is how we can find definite integrals geometrically. Our next lesson will actually figure out how to do that analytically.